Okay, so today will be mostly a repetition of the session which was done a year ago. So what I want to do, I wanted to make a series of sessions about coding interview. And today we will talk about data structures and algorithms. And then on the next sessions, we'll cover many typical coding uh, problems which you receive during the interview. Uh, so the path for this is first to learn about different data structures and algorithms, typical problems, and then of course do a lot of training on LeetCode and other websites. So first, a few words about interview in general. So interview is a transfer of energy and excitement. If you enjoy yourself, your interviewer will enjoy you. If you think good about yourself, I mean, it's all being transferred. It's more about emotions. It's very important to understand. During the interview, project excitement about the company, topics, kindness, good karma. So this is really important. Behave as if it is not an exam, but rather a working situation, and you are discussing a real situation to solve the problem. Uh, you may not know the answer, and I've seen situations like that, experienced it myself, when the problem cannot be solved in the time allotted, or uh, what they actually evaluate on how you communicate, how you discuss, how you approach, how you're collaborating. So when given a problem, listen, repeat, ask questions to make sure you understand it. Make a simple example, ask if you can make certain assumptions, be really curious about finding a really good solution, verbalize your thought process. Oh, have you tried this? Or maybe we could do this. Write a very simple, not optimized solution, brute force. Maybe it's loop inside the loop inside the loop. So the time complexity may be terrible, but that's okay. So you just show that, well, you know the problem is solvable, and then you go on and optimize it. Discuss possible method of optimization, and so on. Test the code if you have ability to run it. Uh, Not necessarily on some interviews, you're just giving a text editor and you cannot run your code. And don't be nervous if you don't know some specific syntax. It's not important. What's important is logic, thinking, and communication. So this presentation will go through many examples of data structures and algorithms. And then next step is to get a lot of practice. There are many websites. The usually good website is LeetCode, mostly recommended, but there are some others like Hackerrank, Educative, Interview Cake. Me personally, I actually paid money to all of them when I was educating myself and preparing. Most commonly recommended is LeetCode. So that's where you find huge community, lots and lots of problems to solve, see how other people solve the problem in different languages, see like memory and speed, and it's really a good area to spend time. And on a daily basis, you can solve 1, 2, 5, 10 problems. Whatever. I definitely solved more than 100. I don't know, maybe less than 200, but I solved a lot of problems on LeetCode, and also I solved problems on other websites. Okay, so there are some good books. Usually, the most recommended is Cracking the Coding Interview by Gail McDowell. I think now she works at Facebook. There are a lot of videos with her on YouTube and typical problems she shows. She uses Java as her language. Anyway, so there are some good books which you can find or maybe download, maybe buy. Okay, let's now go through the meat of this session. So first, array. So elements have the same type and they're indexed. List. So for example, LST with index I. It is like array, but elements may have different types, size, and maybe even complex structures. Like, for example, here you have number, you have string, and you have list as element of another list. Tuple is like list, but immutable, so it cannot be changed. Because it's immutable, it can be used as a key in a dictionary structure or in a set, whereas a list should not be used, or actually it cannot be used because it is not immutable. It can be changed. String, well, maybe in double quotes in most languages. In Python, it can be in single quotes, double quotes, and triple quotes. So it's an ordered set of characters. Sequence, if anything, which can be indexed. So, for example, array is a sequence, list is an tuple, string. They're all examples of sequence. Index is how you number elements of the sequence. Usually start with 0. So the first element of array is has index 0, the second index 1, and so on. If you have two-dimensional array, it may have 2 indexes, and so on. Slice is a subset of a sequence. So, for example, you have a string, mama, papa, and it has element number 0, element number 1, and so on. So this is kind of a list of indexes, right? So if I take slice 2 to 5, in Python, it means include number 2, and then 3, 4, but not include number 5. So it will be 2, 3, 4. 2, 3, 4 is this, ma, and then space. Or 5. 5 not included. Okay, why it says P? 2, 3, 4, 5 is not included. This is wrong. Okay, I have to maybe make it 6. 6 is not. Okay, then it will be true. Anyway, stack. First in, last out. Well, it's like stacking books. You put books one on top another, stacking them. So the last book which you put on the top of the stack, what's called head. Now you can, when you take it, you take the last book, then the book before that, and so on. So it's a philo. Queue is first in, first out. So people form a queue, and if you got your place in the queue early, you will be the first one, the earliest one to go through the queue and get on the other side. Okay, so you can make stack and queue by manipulating a list using append and using pop. Pop in Python allows you to pop from the beginning or from the end. Well, usually it's from the end, but you can indicate the index where you're taking it. So you can as well pop it from the beginning. So you can, using these methods, you can do both stack and queue. So here, there is example using a module called collections, which has a method called the queue. And here how you arrange the queue using this method. But again, you can do it without collections, just using regular append and pop at the first index to the queue. Okay, priority queue. Suppose we create a queue of tickets. Each ticket is described as a tuple with 2 numbers, priority and ticket. As tickets enter the queue, we sort the queue by priority first and then ticket number second. So the tickets with higher priority, which means low priority number, the ones which got there first, will move forward. And within the same priority, earlier tickets with a lower ticket number will move forward. So usually the queue was sorted before adding a new element. So sorting simply means moving the element forward until it finds its place. Usually priority queues are implemented using a min heap structure, which we will review later. Set is a data structure to remove duplicates. Usually, it's done using hashing function, which we'll again discuss later. But the idea of a set is to get unique elements. Like, for example, here we have two sets. One is numbers from 1 to 9, and another is numbers from 5 to 14. And then we do operations between sets. And when we do these operations, we remove duplicates. Like, for example, if we AA or BB, so we combine them together. And there are some elements which exist in both of them. But when we combine them, duplicates will be removed, and the result will be a set without duplicates. So set is unique elements, no duplicates. And this is convenient how you can operate with sets. This syntax is Python syntax. Hash map, dictionary. So stores key value pairs, famous for having constant time for insert, delete, and read. Or when people say in terms of complexity, it's big O of 1. So it's a fixed time complexity, fixed time complexity. Okay, so this is how you create a simple dictionary in Python, key 1 and value v1, key 2 and value 55. So keys has to be immutable. So list or some other object which can be changed cannot be a key. Tuple can be string, can be a number, can be. Okay, so this is example how you add an element. This is example how you delete an element with a key. This is how you decide, well, if element already exists, increase it by 1. Or if it doesn't exist, then create it with the value 1. It's called absurd. And okay, this is example how you can merge dictionaries as the syntaxes of Python changes. Well, you can do it with a for loop, but you can also, now you have these convenient shortcuts to merge dictionaries. Default dictionary, so you can define a dictionary so that when you want to put something there, it already, it has a default value to put there. And well, this is sometimes convenient. How hash works. We make an array of buckets. Well, I call them buckets, whatever. We make an array of buckets. The key is mapped to one of the buckets using a simple hashing function. So this is example of a simple hashing function. The tuple of key and value is placed in this bucket. Reading, deleting the key, same hashing function is used to locate the item. So whether you want to put it there, check if it is there, read it from there, or delete, time to search for the bucket is fixed. It's just you run this hashing function. As buckets fill up, then once you get to the bucket, you need to go through the elements inside the bucket, which may take time. So what usually algorithms do, they increase number of buckets. So you start with 16 buckets, but then when you put more elements, it is rehashed to maybe 1024 buckets and then 16,000 buckets and so on. On rehashing, it takes time because each pair, for each pair, you need to recalculate the hashing, find the bucket where to put it, and then put it there. Okay, consistent hashing. Consistent hashing, people usually don't ask questions on interview about it. It's more about system design, how you make a hash which you don't need to rehash and which you can use in production systems when you need to distribute load between multiple computers and between layers of like distributed architectures. I guess let's keep it for now because we're not really talking about system design here. Okay, Bloom filter was developed by Barton Howard Bloom. So imagine that you have a huge lookup table with millions of words, and we're testing if a word is in this table or not. We may use a huge hash on disk, causing a big I/O, right? Bloom filter uses a small, compact bitmap instead of a big hash. This allows to reject most negatives very, very fast, while allowing very few false positives. These negatives are definitely negatives, but positives are maybe positives. An empty bloop filter is a bit array of m bits all set to 0. There must be k different hash functions defined, each of which maps an element to one of m bits, so set to 1. So if we use k hash functions, we can get up to k bits set. So example, we have m equal 30 and k equal 10, right? To query for an element, test whether it is in the query, feed it to each of the k hash functions, which work very fast, to get k array positions. If any of the bits at these positions are 0, the element is not in the set. You're done. You rejected the element. If all are 1, then it may be positive or false positive. Then you can go and check in, like, well, use some other methods to confirm. So this is Bloom filter. Trees, binary search tree, and there are terms like rebalancing binary search tree, kind of doing rotation from left to right and back. Try is a prefix tree good for words and characters. So for example, R-O-M-A-N, Roman, or Romulus, and so on. So you can put words, and as you edit, you grow the tree, right? So this is called try tree, and it can be used for problems with where you need something like dictionary and you need to do search. Linked list, you have head, you put some data, and then pointer pointing to the next element of list and next element of list. These elements are called nodes, and usually the problems may be well, to go back and forth, or maybe to inverse the list or do something else. Or finding a cycle in the linked list. This is a famous problem. It's solved using turtle and rabbit. So you go over the long list, and one does, like, let's say, 1 step at a time, and another does 2 steps at a time. If they meet at some point, that means that there was a cycle inside the list. So it's called turtle and rabbit. Anyway, heap, binary heap, max heap and min heap. Usually people are not aware of them because it's not a standard data structure inside the language. Like, for example, array or dictionary, hash, set are all standard, but a heap, you have to do it with your own hands. It's easy to do, and it's very, very useful. So the way the structure behaves, it's not a tree where you go from left to right, like smallest on the left, biggest on the right. Rather, it's vertical. Let's say in min heap, smallest on the top, largest on the bottom, and so on. The formal definition is very simple. Each parent is larger than children for max heap, or smaller than children for min heap. And usually what you can do, you can take all your numbers and put them in an array, in one-dimensional array, and then rearrange them in a way so that, for example, the top element, let's say the largest element, will be in 0 index. And then next to children will be 1 and 2, and next layer will be 3, 4, 5, 6, and so on. So you can write an algorithm to heapify in place by swapping elements. And time complexity of building the heap is about big O of n. Push, how you add elements to the heap. You push it to the bottom, and then you start checking against parents and swap until the number will find its place. So push at bottom and adjust. It's a big O of logarithm of n, pop from top and then adjust. So usually the way heaps are used, you arrange the heap and then you take the top, which will be the minimum value in the heap, right? And then you say, well, which one of these is smaller? Let's say this 15. So you put it on this parent and then you compare this, put it, so you readjust and get a valid heap as a result. So when you pop from top, complexity again is big O of logarithm n. And heap sort, so this is one of the sorting algorithms. It has complexity n log of n, and it's a very common, it's a good algorithm. So just for you to know that heaps are useful, and you need to know how to work with them. Different sorting algorithms, I put them in three groups. First is very ineffective, usually have complexity of n squared. So it's a bubble sort, selection sort, or insert sort. And if you look at them, they're usually for loop inside for loop. Next, there are several sorting algorithms which have complexity n log n. Merge sort, heap sort, and quick sort. Well, they're about the same. Quick sort is probably the worst because in worst situation, complexity may be a big O of n squared. So probably merge sort or heap sort are preferred. And then the best sorting algorithm is called team sort. And team sort was implemented by Tim Peters in 2002 and for use in Python programming language. So this is the sorting implemented in Python, and it take advantage of consecutive ordered elements. So if something already pre-sorted, this algorithm takes advantage of it. So the time complexity is between big O of n and n log n. So at its worst, it is like merge or heap sort, but it may be faster. So team sort. Okay, topological sort. So this is how you're sorting jobs. For example, you're running jobs at night, and they have dependencies. Or you're compiling a big system which consists of multiple files. So you're using make to create those dependencies and then compile in certain order. And here is an example. So you have dependencies to create a cup of tea. So for example, go to market, get tea leaves, get milk, right? And then here, start project, boil water, add tea, leaves. So here you need leaves and so on. And at the end, you have your cup of tea. So apparently, you cannot execute this until you executed this, and you cannot do this until you execute, until you go to the market. So the way algorithm works, you identify like elements, nodes on the graph, which are independent, which don't depend on anything. Like for example, go to the market is independent. So you can do it. And you also can do this. So these are the first things you can do. So you put them in a queue. And then once you implemented this, then these two don't depend on anything. So you can add them to the queue as well. So as you go through elements and remove dependencies, and you're adding them to the queue. So this is called a Khan algorithm. And here it is described. And very simple to understand, very simple to implement. Okay, so this is about scheduling jobs which have dependencies. It's called topological sort. Okay, searches. Well, you have binary search, binary tree. You have depth first search or breadth first search. And when you do depth first search, it causes recursion, right? Recursion. And breadth first search, you create a queue. So usually when, for example, you want to find how to go from one place to another, where you have some fences, some trees, whatever, some houses which you need to go around. And at each point you can go, let's say, up, down, left, right, and you need to find a best path to go from one place to another. The algorithm would be BFS, breadth first search. You first look at your nearest neighbors, then neighbors around them, and so on. So you put next cells in the queue, and then you process them one by one. But for certain tasks, recursion is the better approach. But then you go depth first, right? Recursion can always be rewritten as iteration. So this is an example where you have factorial, which calls the factorial, but then you can also do the same thing without recursion, simply as a for loop. Okay, we have just few slides left. Next is algorithm complexity, time and space. Well, big O notation. Big O of 1 means fixed time. For example, it's using hash, dictionary, set. This is fixed time. Big O of n, usually you just go through all elements of something. So it's a for loop. If you go once through this loop and then you go again and maybe go again, so 3 times, but every time it has complexity of n. So the overall complexity will be 3n, but because 3 is fixed, people just say O of n. Now, if you have loop within loop, then it is n squared. Sorting algorithms I've shown you, typically it's n logarithm n. If you have some area which has, let's say, width and height or whatever, several elements, then complexity may be expressed as maybe a multiplication of these parameters. And it doesn't have to be n. Okay. Different approach to solving problems. Sometimes bottom up, sometimes top down, sometimes divide and conquer, maybe binary search, greediness, very common for regular expressions. Okay, declarative versus imperative procedural programming. Okay, functional programming. I had the whole lecture about functional programming. So it's declarative, it evaluates functions, it doesn't set values, it uses recursion, it creates functions at runtime, it passes functions as arguments, it uses pure function, avoiding side effects. Well, okay, there's another lecture for all that. And dynamic programming means memoization, means if you calculated something, you should not calculate it again. So what you do, you cache your results. You can put them in a dictionary. There is also a special module for that. So caching results to reuse them instead of recalculating. Maybe I can do like this, I don't know, reuse them instead of recalculating. Okay. So this is example of procedural, how you calculate factorial using for loop. And this is a functional expression of the same thing. Okay, you're using reduce, which using this function, whatever. Bit manipulation. I remember using it a lot when I was programming in C, C++. I don't really use it with Python ever. Yeah, but you can use each bit of a byte or integer as a flag of some sort, and you can shift left and right, or set them, or do or not operations on them. Okay. Now talking about complexity, solving problems. First of all, a Turing machine. So this is Alan Turing, who came up with a very, very simple abstract idea of the machine. So it's a tape on which you have instructions and you follow these instructions. And instructions maybe go left or go right and maybe do something which is written in a particular cell you're looking at. And there is a table which tells you like with each symbol, what does it mean and what you're supposed to do, kind of translation like map symbol into action. Very simplistic machine, but any operations we do in modern computer can actually be simplified and expressed in terms of Turing machine. So you see the operations, maybe update the cell, move head one position left or right, halt the computation, whatever. Non-deterministic Turing machine. More than one possible action can be taken in some situations. A non-deterministic Turing machine effectively is able to duplicate itself at any time and have each duplicate take different execution plan. Turing complete set of rules, a set which can be used to simulate Turing machine. Okay, so it will be Turing complete. The intractable problem can be solved in theory, but in reality it takes too much resources, time, and cannot be calculated. Okay, time complexity classes. Polynomial time by a deterministic Turing machine. So this is something we can actually compute. Non-deterministic polynomial NP-hard is the class of decision problems to which all problems in NP can be reduced to in polynomial time by a Turing machine, deterministic Turing machine. And NP complete is the intersection of NP hard and non-deterministic polynomial. NP complete is the class of decision problems in NP to which all the problems in NP can be reduced to in polynomial time, whatever. Well, in reality, you don't have to deal with this, but I just wanted you to at least once hear this terminology. Okay, trees. So there's a whole class of problems where you need to find shortest path, or like on each step, you have certain weight. And so you can like evaluate the total weight. So minimum spanning tree is a tree that contains all the nodes of the graph, has no cycles, has minimal total length, sum of weights of edges. Example, a cable company wants to lay lines to multiple houses while minimizing the amount of cable laid to save money. So it's MST. And there are multiple algorithms which are trying to solve this problem. For example, Kruskal algorithm finds edge of the least possible weight that connects any two trees in the forest, right? Okay, shortest path finding used in many like road navigators in your phone and so on. And there are multiple algorithms were developed. I think good to know is A star search algorithm. So it uses some heuristic to try to speed up the search. But anyway, it's good to know about these algorithms, and you can research them on your time. And there are some other algorithms. Okay, this is all which I wanted to discuss today. So on the next sessions, we'll cover typical algorithmical problems which you can meet on the interview. Like, for example, merging two sorted lists. Well, this is trivial. Finding largest word, finding duplicates. We just use hash, right? So this is simple. Function, which is function of smaller numbers, like factorial. Calculate Fibonacci numbers, very common. Do coin change. So how you calculate the change, like how many pennies, how many dimes, and so on. Recursive staircase, how many ways you can achieve certain height. Shortest reach path using, as I told you, breadth first search. Balance parentheses using stack. Queue, how you make queue with two stacks. How you keep contacts in a trie structure. Mirroring binary search tree, common. Finding the second largest value in binary tree. Well, and so on, so on. There are so many different problems. But this is next time. So let me stop the recording.